As desired, our LoRa sensor entities are sending data now. We want to build a LoRa receiver with suitable storage and interfaces to receive and evaluate the data. For this purpose, we use an advanced ESP32 board with LoRa, Wi-Fi and other interesting features on board. In the past episodes, we covered the software and hardware build of our LoRa sensor entities. In addition, we carried out a number of experiments and measurements on solar powering, deep sleep mode, batteries and LoRa RF performance measurements. In the given episode, we will talk about the hardware of our receiver and web server. For our receiver and server hardware, we use the same case as for our sensor entities. In order to pimp the design a bit, I put a printable stick-on label to the transparent front. This is a very easy way to make the design a bit more appealing. With a cutter knife, I cut a rectangular hole into the stick-on label so that we can see the OLED display of the microprocessor board. The little display can only show some important data, like the version number of the software and the IP address, which we need to find the server in our local network using a browser. It also shows the status of the scheduled Wi-Fi sleep mode, as we called it. Furthermore, the display shows the received signal strength of the current LoRa reception and the signal strength of our local Wi-Fi network. In order to verify whether our devices are working correctly, we can also read the current battery voltages and the weather data from the little OLED display. As there is a BME280 sensor inside the case, we needed to drill air ventilation holes into the case. On the top of the case, we have an SMA connector for the LoRa antenna. The 2.4 GHz Wi-Fi antenna is a very small helical antenna that is soldered directly to the ESP32 board. As we do not need an ambitious range for the Wi-Fi, we do not foresee an external Wi-Fi antenna here. On the back of the case, we mounted a micro USB socket, which is part of a 10 cm extension cable that makes internally the connection to the board. While our entity is connected to a USB power source, the 3000 mAh battery shall be automatically charged. The battery shall be capable to buffer for about 24 hours in case there is no external power source. We can also power the entity permanently through the micro USB interface. Since we want to develop the software further when the case is closed, we don't want to push a button within the case for software updates. The entity shall be programmable through the micro USB socket on the back. Our receiver shall receive the data packages from our LoRa sensor entities containing temperature, humidity, air pressure and battery voltage. It shall update its display every 5 minutes. The microprocessor board needs sufficient memory because we want to store data over the year that we want to access via a web browser. Of course, the board shall operate at the frequency that we have chosen already for our sensor entities, which is 866 MHz. The onboard Wi-Fi function of the ESP32 board shall be used to connect our web server to the local network. The scheduled Wi-Fi sleep mode can be activated or deactivated by the hardware switch. The OLED display shall give us information about its status. Why sleep means that the schedule sleep mode is activated. The Wi-Fi shall automatically switch off at 10 p.m. for example. Then after 10 p.m. we find Y off on the display. The entity will wake up the next morning between 6 and 7 o'clock. Y cont means that the scheduled sleep mode is deactivated. Wi-Fi is running continuously. Of course, our plastic case needs to be transparent for our Wi-Fi radio signals. Our BME 280 sensor is glued close to the air ventilation holes at the bottom of the case. Our microprocessor board is really packed with features. The blue boxes functions are all integrated on the ESP32 board. There is a LoRa transceiver, a Wi-Fi adapter, the microprocessor plus memory, a USB adapter, a charge controller for lithium-ion batteries, and a small OLED display. Everything packed on one board. Only our resistor voltage divider, the sensor and the battery are separate devices in the case. As our little board is really a bit crowded, it is difficult to solder the pins. I need to give you a little hint here. You better protect your display leads and other components with thick paper while soldering. Our schematics drawing shows the board's pins and connectors that we need to wire with the switch, the sensor, the voltage divider, the battery, the antenna SMA connector and the USB socket. Pin number 37 is used as a digital in with an internal pull up. Therefore it is high when it is open and the switch will pull it down to low. Pin number 13 and 21 are the data wires of our I2C bus for the sensor. Pin number 39 is used as an analog input that will measure the battery voltage. Now, here we have the set ESP32 board already partially wired. The display is upside down here. On the left side we see a thin coax cable, which is the LoRa antenna cable. On the right side of the picture we see a part of the black micro USB plug. There is a white standard battery connector next to the USB plug. The yellow and orange cables are the data wires to the sensor. The red and brown cables are voltage in and ground for our sensor. Our Wi-Fi mode switch is connected by the green cables. The voltage divider and the battery are not yet connected here. Now I want to share some additional hints on the hardware. Our microprocessor board is just glued to the transparent front from inside. I drilled a small hole to the front so that I can reach still the reset button of the board. The hardware is now up and running since more than 140 days and I didn't need to reset the board yet. Very good, isn't it? The SMA antenna connector is very helpful to test different commercial and self-made antennas. In case we would want to improve the range, a high gain antenna could be used here. On the receiver side, there would be no regulatory restrictions on the antenna gain. The only disadvantage would be that high gain antennas are big and can be pricey. Our sleep mode switch works fine. Unexpectedly, it also helps to reconnect in case the Wi-Fi network is lost for any reason. In case the Wi-Fi connection failed, we don't get an IP address on the OLED display. Then we just push the switch up and down and the Wi-Fi will be reconnected immediately. To me, this happened 3 times during the 140 days period because I operated the entity at a place where the Wi-Fi signal was poor. I underestimated a bit that the ESP32 board and the battery are heating up the case, especially while charging. This has an influence on the temperature measurements of the sensor in the case. During normal operation powered via USB, it reports about half a degree Celsius higher temperature than my other sensors. During charging, the difference can be even more than 1 degree Celsius. And this happens even when I drilled air ventilation holes on the bottom and on the top of the case. After all, I found that I should have mounted the sensor better outside the case, just as I did with the LoRa sensor entities. The onboard charge controller seems to provide a wellness program for our battery. It takes about 30 hours to fully charge the 3000 mAh battery. This is no problem since I'm powering the entity continuously by a little USB charger. And by the way, the charger should be able to deliver a minimum of 250 mA. With one full charge, the entity can run for more than 24 hours autonomously. This is very helpful because we do not lose any data when we need to unplug the entity to change the location, etc. The summary. Derived from our overall concept, we defined the hardware requirements for our receiver and server entity. As always, a valid realization proposal was given. From the experience we made, a few hints for improvements were shared. The coming episodes will cover the software coding of the LoRa receiver and web server. Now, stay tuned and don't forget to subscribe and support the channel. See you soon in the coming episodes.